Hi guys, welcome to the first episode of Selective Attention, which is a new little series Sam and I are starting. Hi, so I'm Andre, Sam is over there.
That's me.
We are two AI researchers based in London. We work for a small AI startup here in London. And our day job involves research, AI research, or more specifically, deep learning research, although we do touch upon certain other things as well. Day to day, we have to do a lot of paper reading. We read papers all the time. And as I'm sure that anyone else who reads papers knows, you oftentimes either just completely miss certain papers or you do end up reading them but then forget about them soon after. Everyone has their favorite papers, and what we want to start doing to benefit not only ourselves, our company, and also maybe you guys, we want to start documenting some of the papers we have read and which we have enjoyed and which we think are interesting. So the paper we have in front of us today is called Unsupervised Learning by Predicting Noise. It's a publication by FAIR. Facebook AI Research is by Piotr, Bojanowski, and Armand, Joulin. And we will spend the rest of this video just going over it. Just really quickly before we begin, this video series doesn't assume much prior understanding, although it does assume a very basic understanding of machine learning and also a very basic understanding of the sort of parts of mathematics which deal with machine learning, including linear algebra and probability theory. Although we'll try and make this entire series as intuitive as possible. Both Sam and I are very visual learners, which means that we will often describe concepts as visually as possible. So hopefully, even if you're not well versed in certain areas of mathematics, you'll be able to tag along right up until that point. Right, so I guess without further ado, let's start describing this paper. Sam, can you tell us something about the motivation behind this work?
Yeah, so I guess really briefly, we can just talk about the sort of area that this paper is in. So this area is, I guess, latent representation learning or representation learning. The idea here is that we want to, from complicated data like images or text or video, we want to be able to find a way of getting that very high dimensional data and finding some sort of representation that is meaningful. And we want to be able to do it without knowing anything about the image. We don't want any labels. We don't want anything else to inform how we should find these representations. So I guess very briefly, a lot of you guys should be familiar with autoencoders. So autoencoders, basically you have your X, which is your data. You have a network that takes it to an encoding, which is very, very small. And then you want to get from that encoding back to your X. And the idea here is this part here, this kind of this arrow to the embedding here is a function that will hopefully find from your very, very high dimensional data X a very, very meaningful E. So this low dimensional E might have some high level meaning to it. We'll be able to use that to understand something about the image, say.
So just again really quickly, what autoencoders do is they take some input X. They then use what's called an encoder function or an encoding function and map this input into some latent embedding space, which is represented by the E here. And then from that space, they decode it back into this X prime, which, depending on the way you set this up, you usually want to be as similar as possible to the input. So usually people will try and use what's called a reconstruction loss, and we'll try and match the output of their model back into the input in the hope that what's happening in this space here is somewhat useful and somewhat meaningful.
Yeah. So this E, if you think about the size of it, the amount of information you can have in it, is much, much smaller than this x. And the idea is this sort of information bottleneck forces this encoder network to extract very high level features from the image, say, and that's what's left in the E. So that's autoencoders. And the reality is they don't really work that well. They work okay, but they're not that great. The next thing I guess you have are variational autoencoders. Now they have an X as an input. They have an encoder function that returns you a sort of probability of your instead of a Z, instead of an E, we're going to call it a Z. It's actually a probability of Z given your X. Sorry there, I'll just, and it's variational in the fact that we instead of having this concrete representation E, we now have this sort of probability distribution for our encoder representation. And usually we have this kind of prior structure of Z. So here we want to say, actually, if we got all of our X's and we pumped it through this encoding function, the Z's have to be distributed in a way that satisfies some other distribution. So we'll say maybe if we get the whole of our data set and we compute the Z's for each of our X's, it must match very closely to a Gaussian distribution, a high dimensional Gaussian distribution or something. And there's a bit of a methodology into how we get that to work. But then from this P of Z given X, there's a bit of other stuff going on, but for just to keep things simple, we then produce a P of X given Z here. And realistically, this is also just a reconstruction loss. We're just trying to reconstruct X from our Z. The only magic here is that the only extra thing here is that we have a constraint on the encoded space here.
And I guess again, just slightly more concretely, you have an input, you pass it through an encoder function. In the usual case, although there are sort of different architectures of this, but in the usual case, this network, this encoder function, then outputs the parameters of this distribution. So in the case of a Gaussian, that's a mean and a variance or a covariance matrix. And then these Zs, these latent representations, are actually sampled from this distribution and then used as points in space which are decoded by a decoder function, this guy here, back into something which you want to look like your input.
Yeah.
So again, very similar to the way autoencoders work.
Yeah. And so again, if we want to look at where in this VAE could we use what part of this network, what part of this model could we use to extract high-level representations? It's again this encoding function here. So if we now at the end of training we can sort of drop these decoders, we can use this encoder, we can use this encoder, and the sort of features, the output of that encoder network should be somewhat meaningful, and we can go on to what that might mean later.
So just super quickly, right? I guess what's really interesting about these guys, right, is both autoencoders and variational autoencoders, is that if you're used to supervised machine learning, right, where you're given X's and Y's, right? Well, these networks, their outputs actually try and mimic the input, and given the input, they're trying to produce this output. So really, you can think of these outputs as the targets, which you want to approximate. Like they're sort of like your Y's. The only difference is that this data need not be labeled, right? You can have a data set of only input data without any labels, and both these methods work. And that's unsupervised learning.
Yep. And then you have one more form of this, and it's slightly different to the two, which is let me just get that in frame, is a GAN. So GAN takes, you have some noise, you push that through a decoder function to give you sort of X prime. You then get some real X's, and then they both go through a classifier, which is asked real or fake. Right, fake. Yep.
And what decides whether it's real or fake?
So the thing it has to try and classify is it has to say, I think that this X prime is generated, and I think this x is real. And the idea is that then you then have an objective of this arrow here, this from z to x, to produce as realistic images as possible, and for this guy here to learn as best as possible which is real and which is fake. So when it comes to what can we use to sort of extract good representations from images, this decoder function isn't useful because it's a low representation to an image. It's actually the discriminator. So this guy here. So this is the other thing that we can use to get good representations from in an unsupervised way. And actually what we do is, because this is a prediction, what we'll do is we'll kind of chop off the last few layers and we'll use some sort of intermediate representation here. So that's kind of what else is on the market when it comes to this paper. And this paper does something very different. And the idea is that there is no decoding. There is no act of trying to recreate the image from a low-dimensional space. What you have is an X, and you have an encoding. And I guess we're going to should we just call it Z for the time being? And so basically you have this encoder function. And then what you have is this big hypersphere of Y's. I'm going to see if I can do this properly. And the idea is that you have to match your Z's to specific Y's on the sphere. And this might not be the most intuitive drawing, but we'll sort of, I'll get into why this works and how this works in a little bit. But essentially, you essentially have a fixed number of targets. So in a supervised setting, imagine you have a fixed number of labels. But the thing is, these labels can move around. And what we do is, as we learn this encoder function, we learn how best to fit the labels to the images.
Yep. So maybe again, just to reiterate here, we have some inputs x. We then have a function which takes these x's and maps them into these z's in some latent space here, and then within the same latent space, we have a bunch of what the paper calls targets. You could call them labels because they're actually used just like labels. And what you want to do is you want to bring your z's in latent space, which are just the mapped x's. So you want to bring your z's in latent space as close to the y's as possible. And all of this unfolds in a very, very constrained space, which is the unit hypersphere. And I guess what's really interesting about their method, and you'll see this in a minute, is that at every point in time you can actually sort of reassign which target, which label, which Y you're trying to move a respective latent representation Z to.
Yeah, and the most important thing is it's one Y to each Z.
So it's a one-to-one matching.
So you basically have a bunch of Y's that are dotted around the sphere, and you have to, for each one of these Y's, you have to make sure that only one Z is close to it, really, and another Z is close to another Z, etc., etc. And basically, what you have is a way of saying the entirety of all of your data must uniformly fit around the sphere. And in order for you to do that, you need to find a way of differentiating between x's in such a way that you can perfectly uniformly kind of cover this sphere in your kind of in your latent representations. All right. So I guess just before we go into the full mechanism, I want to just give you a brief idea of what you can do with these latent representations.
Yep.
So what they do in the paper and what they do for their results, the way it kind of works is, let's assume we have our trained function. So again, we have our x, and this is our encoding function here, this arrow, that is been trained, and it's just great. Let me tell you, it's fantastic. We've got the sort of latent representations coming out of this are, extract such great information about what is inside ImageNet, say, that it's almost like perfectly the labels of ImageNet or something like that. And what we'll do is we'll just freeze this network, and what we'll put here is just a MLP, so maybe a 1 or 2 layer fully connected bunch of neurons, and then we'll ask it to make predictions, right? And so what we'll do is we'll get a small subsample of something like ImageNet, maybe something like 1,000, 10,000 of them. I think 10,000 is what they use. And they train this MLP on the latent representations of X and see how well they perform. And so the idea is that you can actually have a very, very large and unlabeled data set, train a network in such a way as they do in this paper. And then you only need a very small labeled data set to which you need to train something like this MLP to get from your latent representations to your predictions, and you actually perform quite well.
So again, we have some inputs, some images. Using their method, we find their latent representations and learn those latent representations. Which moves these latent representations around in some latent space, such that given your sort of constraints and your loss and a whole bunch of other things, it somehow ends up making sense. And then by feeding those latent representations to a simple classifier and training it, given some actual genuine labels this time, you can use this as a form of pre-training. To do even better on certain just classification tasks.
Yeah, cool. So shall we jump into how on earth does it?
Yeah, what does all this mean? what is all? I mean, you must be so confused.
Yeah.
The first time we read the paper, and by the way, this will probably hold true for all of you. There's a great art to how you read papers, and the simple truth is that, for the most part, you'll never be able to understand a paper in a single go.
Yeah.
So it took us quite a while quite a number of times to understand this paper in detail.
Yeah. So let's go and the way that I explained this to Andrew after I read it, really there's 2 steps, and the first step is initialization, and what they do here is for each X. Sample from an L2 sphere, and that's the Y for that X. So for each Xi, your Yi is just a sample from that L2 sphere. And what we'll say is that might be something like, I think in this paper it's 128 dimensions. Right? And just to be concrete, what this means is that you have your Y will be a vector where basically the L2 norm of Y, the L2 norm of it will equal 1. And it's just a random noisy vector from that space. So that's the first step. So what you have now is a bunch of X's and their corresponding Y just being a random position on this sphere. Right? And then you have the training step. Oh, we're running out of paper. Let's try to get this go. So you have the training step. So for the first thing you do in the training step, I guess a way of thinking about it is you have to get a random batch. Right. And in this random batch, you have your X's and you have your corresponding Y's. Right? And we're just going to put them as matrices for the time being. And you'll see why in a bit. So we then compute this f of x, or f of x, right? And so what you have here is a bunch of z's, which are in the same space as y. So actually these z's are also L2 normalized. So they're the output of something like a big convolutional neural network. They are also 128 dimensions as the output of the network. and they are also L2 normalized, so they exist on this on this sphere. Now, instead of just saying, well, now the loss is z minus y, so we actually reassign the y's. We actually kind of shuffle these y's around corresponding to these z's. So we then find the optimal assignment. Of z, of like sort of y, I, z, I guess. And we'll go onto that in a little bit. So, what on earth do I mean by the optimal y, I, z, I? So, let's just imagine that we forget how the y's are assigned to the x's initially. So before we pull out this batch, we have a bunch of x's and a bunch of y's that are assigned to each other. At the beginning of this batch training, we kind of forget about those assignments, and we just assume we have a bag of x's and we have a bag of y's, or a bag of z's and a bag of y's. And we have our L2 sphere. Now,
so this is in 2 dimensions.
So instead of 128 dimensions, let's just do it in 2 dimensions. So this is the perfect circle of a sphere. And that means that when we have a bunch of images in this batch, and we look at the output of these images into this latent space, we might get something like this. So we have one latent representation here, another one here, another one here, another one here, another one here.
So these are my different z's.
Yep.
Over here.
And we then are able to picture where the y's have to be in our space. So let's just say we have a y here, and we have one here, and we have one here, and one here, and one here. And what we want to do is now assign the y's, these circles, to the z's, which are the x's, unfortunately, in a way that we minimize the total loss, the total distance between the y's and the z's. So what that means is if I measure the distance between these two, if I assign these two together, assign these two together, assign these two together, assign these two together, etc., and I summed up their distances, I want to find the optimal pairing so that we have the smallest distance. Actually, I lied a bit. It's not distance, but it's the distance squared. So what that means is with the distance squared, if you have if you're really far apart, the penalization is going to get much higher than it is if you're close together. So here's one I made earlier. Actually, no, this one, it's not too difficult. If we actually, can I borrow that pink pen of yours? Thank you. So the optimal assignment looks something like this. So this Z is assigned to this target. This Z is assigned to that target. This one to this target, and then we're stuck with these two here, right? So if we consider this Z here, it's actually quite close to this target here. But if we assign these two together, this Z here has to assign itself to this target here. And that's really far, so that loss is going to be huge. So even though this Y is closer to this Z, we're actually going to assign this latent representation here, and this latent representation here. And from this assignment, we now have our new targets. We don't even need to know how they were assigned beforehand, but we know how to assign our targets in this batch. And via the magic of backpropagation, all we have to do is calculate the losses between these targets, and we have our way of training. Now, I just want to very quickly say something that's kind of interesting here is this decision process of where we assign our targets is completely discrete, which initially makes you sort of smell, oh no, this isn't backpropagationable, how can you do that? But the fact is that deciding what the labels are can be as weird and wonderful as you want. It only has to be the loss function that has to be differentiable. And here we can just constantly reassign these z's different targets during training. It's perfectly fine so long as the loss, which is this distance, is differentiable.
And I find that really fascinating, actually.
Yeah.
I think that this is definitely food for thought in terms of how, maybe in a completely different context, something like this, could be used. So remember, this is done using the Hungarian algorithm, which is a bipartite graph matching algorithm. Remember, we have, if you think of this as a bipartite graph matching algorithm, we have our latent representations lined up on the left, our targets lined up on the right, and then we can draw edges between these two sides of this graph. These edges represent which latent representation we assign to which target, and the Hungarian algorithm assigns these edges in such a way as to minimize the sum total of distances between these two sides of the graph. Now, I guess what's really interesting is that that's the Hungarian algorithm, which has nothing to do with modern day deep learning. It's not differentiable. Mm-hmm. People haven't been using it in their models and so on. And this idea of essentially having this reassignment, this discrete reassignment step, which in no way impacts the differentiability of your model, I think is something which more people should be looking into.
Yeah, 100%. So yeah, I guess we can just round up the training. So we now have our targets, we now have our loss, and this being the recursive step, we just keep doing this. So we keep doing this with batches. We get a random batch of examples. We compute the z's. We find this matching to their new y's, and this is all inside a batch of examples in the algorithm. So we're still keeping to the deep learning scalability. Keeping things in batch sizes, scaling it to larger data sets, and essentially we just keep on doing this and doing this and doing this and doing this until the loss gets smaller. And when the loss is small, that means that the distance from a x to a z to a y is very small. And that by virtue means that you must have a uniform mapping around the sphere.
So just a really quick question, right? Which might sort of clarify a thing or two. When is the loss optimal? When is the loss zero?
The loss is zero when for every x, it's z, i.e. the output of this neural network, is exactly the y that it is assigned to. And by virtue of the fact that these y's are kind of dotted around the sphere, it must then exhibit the entire mapping of the dataset to this hypersphere must be uniform. So it is like a dataset wide regularizer, that it must uniformly occupy the space that we have designated by the y's. Actually, a little sort of footnote. If you're wondering why we use why use a sphere in this, why use a sphere? Why not use something like a sampling from some isotropic Gaussian, like a VAE or something for this?
Or a cone.
Now, seeing as we don't have any other signal, so the whole idea here is that the entire neural network is just mapped this latent space. If we just have a point cloud with a center, the neural network will just learn to map everything to the center and will kind of get stuck in this rut. And by virtue of it being a sphere, you're kind of forcing it to learn a representation that isn't just a single point. It sort of is a bit more friendly as a space. So I guess we can just finish. Oh, do you want to say something?
Yeah, I was just going to go to the next section. I mean,
yeah.
Do we have anything else to say?
The only thing I was going to say is just show from the paper, so we can show some stuff from the paper. So what they have here is some images from ImageNet. And what they have is, I think the top row here are just, they basically pick a random image from ImageNet. They compute its latent embedding, like what its latent representation is. And then they look at the nearest neighbors in their data set from the other embedding spaces. And they find fairly similar objects, which is really cool. You could almost see it as a form of like image search. Image search around this sort of sphere. which is quite cool. So that's like sort of, you don't just have to take our word for it. This is the end result of training a network on ImageNet is. Yeah.
All right. So now that we've been through the motivation behind the paper, you hopefully understand some of the intuitive descriptions we've been giving you. And I guess what's really interesting about this paper is that it actually relates to a whole bunch of other stuff. So what else can it do?
So one of the things that we were thinking about, we were just speaking about how this noise as targets paradigm allows for a dataset wide, like a sort of whole dataset wide prior regularization. So if you want to have a prior distribution of points, and you want your latent representations to perfectly match that prior distribution, the way that you do it with noise as targets is that at the end, every one of your latent representations is tied to one of these points sampled in a very, very large manner, like a very, very large number of points from this prior distribution, and you have this one-to-one mapping, which means that if you have a distribution that you want your entire data set to behave as, I want all of my latent representations to be isotropically, to follow an isotropic Gaussian distribution, you can sample lots and lots of points from this isotropic Gaussian distribution and say, well, as we're training, we're going to be updating these assignments until we have a mapping from this high dimensional space, this high dimensional input X, to these low dimensional latent representations to which it must perfectly fit this distribution. Now, one of the areas where this is important is VAEs. So in VAEs, you want to have a way of making sure that your distribution of your latent representations is isotropically Gaussian. So one of the things we're kind of thinking of is a sort of NAT VAE. So similar to the way that we described a VAE, a variational autoencoder, you have your X, you have your high dimensional input, you have your encoder that produces a latent representation Z, and you want that latent representation to then have be able to be decoded into a X that's very like an output that's very similar to your input. And with a VAE, you have a prior distribution on this Z. Now, the way it's done previously is you sort of have a parameterization of a distribution of your Z, and then you have this penalization term that says how much that distribution of your Z doesn't follow this isotropic Gaussian or something, for example. And this loss term has to be differentiable. What we could do instead is then just sample lots and lots of Ys from this normal distribution, and then just use noise as targets to sort of align these Zs from your network to these Ys perfectly. And what I mean by perfectly is that the entire data set, if you got all of your X's and you then produced all of your Z's, there must be a one-to-one mapping to this very, very large bunch of samples from this distribution in a way that you kind of perfectly occupy this space. So you could just have a bunch of Ys from a normal distribution, as you do in variational autoencoders. You could really, one of the things that's really crazy about this is you could use any distribution you want. You could, have a distribution of points that look like Donald Duck. You could have any sort of crazy distribution of points, and you would then have to say your the whole data set of Zs, if you think about it, must align perfectly one-to-one with these Ys. For those in the know, this is actually really, really similar to the work of adversarial autoencoders. So you could do something very similar with adversarial autoencoders, in which you, instead of having this noise as targets for your Y, you have a discriminator to say how much you think your Y differs from this latent distribution. But the reality is you wouldn't even have to have a normal distribution here. You could have any distribution and then make sure that your Z's align to it. And then you have now a joint objective. You have an objective of, I want to encode my X to a Z, and then I want to decode it to an X. And I want these X's to be as similar as possible. And at the same time, I want the total distance of these Z's to my Y's to be as small as possible.
And this is a really cool idea, right? Because Whereas in VAEs, I have some inputs, and then I have an encoder function which then parameterizes a distribution from which I sample my latent representations. In this case, the sampling is actually done at the very beginning, and it's done only once. So it's almost like, ignoring all the other cool things you've just mentioned, it would also be just really, really easy, right, to like switch around this distribution and then just use the architecture you already have to then move your Zs closer to the targets you've just sampled from, whatever distribution strikes your fancy.
Yep.
Which is kind of cool.
And at the same time, previously you have to sort of conjure up, you have to figure out a differentiable loss function for your Zs. So in VAEs, you basically have a per example loss function for your Z. So for each example, the loss function is independent. Whereas here, the loss function is dataset wide, if you think about it. It's not like everything has to be isotropically Gaussian-ish. It's everything must fully occupy as a dataset this distribution. I think that's one way that this noises targets could be utilized even more. There's actually another area that I think would be really interesting as an investigation, which is a sort of a way of augmenting this sort of semi-supervised learning technique. So let's consider we have a bunch of information. Let's say we're trying to predict people's height. We're trying to predict the height of a person based on some categories. So we might have something like age, sex, income, maybe something weird like that, where they are in the world, how many children they have maybe. And you have a bunch of categorical information about them. And for a very small number of people, let's say we take 10,000 of the entire population of the world from all different shapes and sizes in different parts of the world, and we know their height. And we also know this information. So in a way, we have this very, very small labeled data set. Now what we could do is then train a model to predict predict the height from these features, and then use it in a way to kind of extrapolate, use that function to predict everyone else's height from these features and see how well we do. But we actually have more information about people's height. So I don't know the full figures, but we know that people's heights kind of follow a rough normal distribution. Right, so at some point you have a mean distribution here, and you have a mean height, and you have a standard deviation, and you know that the entire global population of the world fits this distribution. So what you could do is then say, well, let's get this same categorical information I was talking about before for as many millions and millions and millions of people as we can. For each one of those people, we generate a noise target from this prior distribution. And then for this small frozen set of examples, we know their height. So you then have the noises targets trying to align themselves to this distribution, and at the same time learn that we might have a label here, we might have a label here, and etc. here, and here for specific x's. Right? So we then have a sort of labeled problem, which is this like f of x must kind of equal some sort of y known, and we also have this f of this kind of other large dataset x prime must go to a kind of y nat of the global distribution. And so we have this kind of joint problem of for the known examples we want to train in a completely supervised setting, and we can kind of maybe augment our knowledge or kind of help ourselves by saying, well, we can actually sort of align these y-nats from this initial sampling from the global population distribution to something that we think fits corresponding this x. And I think that would be a really great thing to investigate to see if this improves upon a sort of just vanilla unsupervised learning or just using this known data set. And I think something like this might be a really interesting place for investigation. Yep.
Great. So here you're essentially saying that you wish to pre-populate, right?
Yep.
Some of your targets with fixed targets you already know of.
Mm-hmm. Yep. And that this kind of small data set, this kind of y known and this maybe x known or x sort of to the known data set, informs this kind of secondary training objective, which is we want to sort of align these noises targets wise from this global distribution to this very, very large unlabeled data set. And the question is, would this maybe work in a way, would this perform better than if we used just this distribution? So if we just trained on this distribution, would we get a higher performance? And also if we used this unlabeled distribution in an unsupervised way, just like we used a VAE or an autoencoder or something else as a way of kind of pre-tuning the network to then perform better on these, that's a very common technique. The question is, would this combined technique work better than sort of this separate technique of unsupervised and then supervised, or just supervised? I think we haven't had the chance to work on this, but I think something like this would be a really interesting area to investigate.
All right. Well, I guess that's it. I mean, hopefully you've now gained a better understanding of this paper. By the way, this paper is from 2017.
It is April 2017.
April 2017. So was it presented at ICML?
I actually do not know, but
I think, but don't quote me on this. This was an ICML paper, which means that it was probably worked on in 2016. It doesn't yet have many derivative works, but it's definitely something which people should be acquainted with. There have been a couple of blog posts even about this paper, and we're really excited to see just some of the research that hopefully will be coming out that relates to this work. Hopefully you've enjoyed this short video. Well, rather short video. It's probably quite long, and hopefully you're not too. You haven't been sort of too bamboozled by the two of us, and hopefully you'll get to follow us some more in some of the upcoming videos we have planned. The format will usually be very similar to the one we used here, so we'll be going over some of the papers that we find interesting, that inspires some of our work, and that hopefully you'll find interesting too. So I guess that's it for me.
Yeah, and it's goodbye from me too.
All right. Nope. Bye bye.